Hello, y'all. Like Sarva said, welcome to the very first review of Tilde 5.0. We will be starting off with our project Mushroom. To what the project is, what inspired it, what we did the last week, and what we're going to be doing next week.
Yeah. Okay. So what is Mushroom? Mushroom is basically a lightweight terminal-based text box, which is hosted via an SSH server to ensure it's encrypted and secure. All you really need to do to join the chat box is to enter one command into a Unix terminal, and you'll enter inside without any other external installations. The concept here is it's all hosted via an SSH server. This SSH server only checks for your key pair to join. So every device has their own key pair. So with this key pair, we can make a distinction between users and regulate the flow of users trying to enter into the chat box. And here's the screenshot of Sazau's assets, which I'll talk on later. So about Sazau's assets, basically, Sazau's assets is also a terminal-based chat, but it relied heavily on command line commands to perform basically every task. And it also had a very bare bones structure of a UI, so it was kind of hard to navigate through it. Here are the list of commands. Okay. So about our goals. So the idea is to build on top of Sazau's assets. We thought of implementing our own functional features and as well as implementing a better UI. So it'll be easier for the user to actually comprehend and navigate through the app. So for our tech stack, this will be mainly written in Go, where we'll be using two frameworks mainly. One is this, which will help us to host the SSH server. This is basically a boilerplate, which helps us actually set up the connections, authentication, and the rest of the terminal setup. And for the UI part, we will be using Bubble Tea. You can see an example of a terminal formatted Bubble Tea over here.
Okay, so like Tanmay said, we'll be using Go as our tech stack to build this chat. The thing is, we spent the last whole week learning about Go, and there are quite a few fun facts about it. So it began to be developed in 2007 in Google when three developers saw that Google has a large scale of operations. So it needs a language that's pretty efficient, but also easy to program in so that it can help those large scale operations. But there was no language like that at the time. So that's why they decided to come up with Go. The production was done around 2012, it finished around in 2012. So the features that Go has kind of helps what they were looking for in the first place. The first feature being a simple and concise syntax. It is similar to C, so it's familiar, but it also only has 25 keywords. So it's pretty easy to memorize and work with and very versatile. Another thing is concurrency constructs. So concurrency means being able to do multiple tasks at the same time, which is very advantageous when you think of large scale operations. This is implemented using Go routines. So what Go routines does is exactly what I explained earlier. It can run multiple functions at the same time, multiple programs at the same time. They also have this thing called channels, which Go routines use to communicate with each other, which is again something that's very advantageous. We will see how we use this in our chat very soon. Compilation to machine code directly. So this is a feature of C. There's no VM in between. It's directly converted to machine code, which makes it very efficient. Another feature of it is its memory management. So it's not as freely manageable as it is in C. Like we're able to play with memory very freely in C. Here, what happens is it has a garbage collecting system. So it has safety checks like array bound checks or initialization. So it makes it very safe to play with for something that's very large scale. And finally, the most advantageous point of all is the fact that you have modules in Go. So commands like go mod, go get allows you to use either external packages or packages that you create on your own, which makes for very organized code bases. And that's exactly what they were looking for. Now, why do we choose Go for our SSH chat? First of all, it has this package called crypto/SSH, which has the means to verify the identity of the chat server, first of all. If you have used one before, you know that when you add the command into a terminal, it first identifies the key of the server, and then you get into the server. So that's there, and it also has inbuilt functions for verifying incoming clients using their internal key, like Tanmay explained. Another advantage is Go routines, like I said. So how Go routines works here is when a user logs in, they have a lightweight Go routine that's attached to them. So when they send a message in their Go routine, that is traveling through channels to reach the main Go routine. And that fans out to every other Go routine, and that is every other user that's logged into the server. That's how a chat server works. And finally, of course, like we mentioned before, libraries and frameworks. We have Wish that's exactly for building SSH chats, and we have Bubble TTY, which has a lot more scope than we thought of earlier. You can have buttons, you can have a whole setup that looks like a website all in your terminal without downloading anything else. Once we were done with that, we looked at the requirements of what we need for our chat box, chat server. So we obviously took inspiration from Shazam, but we also had added our own features. So the basics that we really want is commands like a welcome, sorry, slash help, slash exit, the basic stuff that we saw earlier. The features that we want, though, the ones that we added on our own, was to be able to create a room. So in Shaza, what happens is you can either talk to everyone that's in the server or you can message someone personally using the slash message command. What we want to do is kind of create a function of groups. So when you do slash create room, you create a room, you can either add a password with it or not. And there, whoever joins in using slash join room, you can text to just them. And you also have slash room to see the available rooms. Another fun function that we wanted to add is emojis. So if you're familiar with Discord, you know that if you do :sob, you get the sob emoji. So we wanted a functionality like that for people to use emojis in their chat. And of course, chat slash emojis to see which ones are available. The extras are something, if time permits, we wanted to add something like slash away, slash back for online status, and etc.
Yeah, and what's for next week? So by next week, we plan to actually learn how to build a terminal UI with Bubble Tea. And also with that knowledge, we also plan to make a basic app using this Bubble Tea UI. Yeah.
Thank you. We'll be back with more cool stuff next week.
All right. I hope my mic is working. Can
Yes.
someone yeah. Okay, I had a few questions. So
Mm-hmm.
you guys mentioned how you use the keys to kind of identify different users, right?
Mm-hmm.
Um, w- is it possible for me to share my key with someone else? If that's the case, what if me and my friend are using the same keys? Can the server distinguish who's who at that point?
It, as far as we know, SSH keys are associated with emails. So if I have a key that's associated with my email and I use that on my computer, it's there on my system, I can log into that server with this key. So that's how it works. That's what we know as of now.
So are you saying I can't generate an SSH key if I don't have an email address?
I'm not entirely sure about that. But the one key that I did generate myself, I did use an email.
Yeah, you should probably go and read a little bit more about that.
Uh,
Um, yeah,
yeah, actually, you can generate a key using any text combination. It doesn't have to be an email.
yes.
So
One
you
more.
could, yeah, technically exchange with your friend. Yeah.
Yeah, so at that point, I was wondering if there was any other mechanism where the server can identify separate users.
Yeah. As of now, it's just by your SH key. We'll maybe decide on that later.
Okay, cool. One more thing. You guys, talked about Go routines, right?
Hmm.
Um,
Yeah.
so it's pretty nice that you guys are going with Go. You have Go routines to help you with this. But I was kind of curious if this would be possible in a language that doesn't have such strong concurrency like Go. Or like, did you think of any other languages before settling in on this, or did your mentors just say, yeah, we're using Go, and you guys didn't question it?
We didn't exactly question it because they did tell us that we will be using Go. But going through it, we understood why it's advantageous to have it in the first place. Go routines are pretty lightweight, and when you have so many users getting into a server at once, you need something that's that lightweight and can work at the same time simultaneously. So, Go is a pretty ideal language to use for this case.
All right, makes sense. Cool.
There is a question in chat for you guys by Vinayak. Has that been answered?
Oh, wait.
Um,
Sorry, we didn't see that.
yeah, I'll just read it out. He's just asked if you're using bubble tea for TUIs, why use commands at all? You could have different buttons for important features.
Yes, so we had that idea. This is just the functionalities that we want, and we noted them down in terms of commands because that's what we're familiar with Shazam's chat. But we do have plans to integrate buttons when we can and where we can, but we're not entirely sure of which one should be a button, which one should be a command, because both are convenient in their own ways. So we will be figuring that out when we use Bubble Tea next week. Vinayak, does that answer your question? Yes, Selva, that's what we're going for. Like we mentioned earlier, what we want to do is take the skeleton of an SSH chat, which is Shazam's, and kind of make it unique in our own way by creating a full-on UI for it. So even without downloading anything external, you're able to have a full-blown chat app in your terminal. Okay, so a TUI and GUI. A GUI would be a graphical user interface that's kind of external, right? So, for example, Discord itself, what you're using right now is a GUI. So you're able to unmute, mute, or enter messages, whatever that is a graphical UI. A TUI is the same thing, but in your terminal, nothing external. All you have to do is enter the command and you're directly in the server. So, like I said, there's another thing you can check out. I will type that in the chat. If you enter that in your terminal, you will be directly dropped into a place where you will have different links for everything that Bubble Tea and the Charm framework has helped with. So you can see it is a UI on its own. You did not have to download anything external. To answer Selva's question a little more clearly, in terms of GUI, TUI combined, what you can better phrase it as is we want some functions that you can easily access with the TUI, but also as a command. So whichever is preferable for you, you can use that. Is there a message history? Okay, I don't think there is a message history. We're not sure how we're going to implement that concept if it is there. But in Shazam's chat, what it is you just drop into a server and there's messages. There's no way of storing them. But yes, any other questions?
If there are no questions, I think we can go to the next one, which is Ziguana. Thanks a lot, Mushroom.
I'll share my screen once. So can you guys see the screen?
Yes, we can.
Okay, thank you. Good morning. I'm Aniket along with my teammates Abhishek, Karnav, and Tanishk, and our mentors Sankhya and Ashton.
we are proud to introduce Project Ziguana. When we started off, we had a fundamental architectural choice, that is either build a compiler from scratch or build a transpiler, and we chose the transpiler route. Building a traditional compiler means reinventing the wheel with a massive backend, but by translating our language directly to C, we keep our architecture radically simple. We use tools like GCC to handle the heavy hardware optimizations, and we gain a direct path to seamlessly integrate the massive ecosystem of existing C libraries. This frees us to focus entirely on the front-end developer experience. As you can see, the pipeline is very seamless. You write your source code in R language using the .zg extension. It flows directly into Ziguana, a transpiler made on Zig for absolute memory control and performance. Ziguana actually translates that code into standard C text and automatically hands it off to GCC to compile the final executable. Coming to our language ecosystem, it is statically typed and intentionally uses a familiar readable C-like syntax. We have tried to strip away as much as friction possible. Out of the box, it features native types, arrays, and seamless string interpolation. But we are trying to build for the future, so our roadmap includes custom types like structures and enums, full C interoperability, and type inference. The foundation we are trying to achieve is robust. But to truly appreciate it, we must understand how it works under the hood. So I'll hand it over to Arnav.
Can I next slide? Yeah. Hi. So from this slide provides a high-level overview of a language's grammar using EBNF. EBNF stands for Extended Back-is Now form. It is a specialized code notation used to define the exact syntax and grammar rules of a programming language. So at the top of the diagram, we see the program. It represents the source code, and it is made up of functions and statements. A function contains a block of code which is enclosed within braces, and it is made up of statements. So right now our language supports variable declaration, assignment, if statement, while statement, and a print statement. Statements can also have expressions, and these are in a hierarchy which enforce a natural operator precedence. And so this diagram basically gives a bird's eye overview of our language. Have next slide, please. So this is an example program in our language. So each program has a entry point from a main function. The fn keyword is used for the function, and a return type, which over here is void. So this code snippet also shows the loops in our language and string interpolation. As you can see, the syntax is similar to C, and we also have features such as we also have maths operators such as assignment and comparison. Can I have the next slide, please? So this slide illustrates the overall architecture of a transpiler. It's inspired from the book Crafting Interpreter, the chapter map of the territory. It has a mountain analogy. So as we climb up the mountain, we go from the raw source code to the AST, which stands for abstract syntax tree, and then we descend again to the final binary. So the source code undergoes lexing, which groups us into tokens. And then these tokens are passed on to the parser, which construct the abstract syntax tree. And this is converted into a corresponding C code, which is sent to a compiler like GCC to make the final executable. So that's it from my part. Abhishek will be continuing from now.
Sure. So the first part is Lexer. So the Lexer does is it takes the unstructured raw source text, it reads the ZG file and breaks it down into a stream of tokens like keywords, identifiers, operators, and literals. And this part even does most of the filtering. So let's say we have some unnecessary white spaces or some indentation. This part mostly removes that those noise. Next slide. So next part is the abstract syntax tree. This AST is the part of the parser. So now we have the tokens. stream of tokens. So the parsing engine, what it does is the parser takes the flat token list and validates it against our language's grammar rules. So, and it even handles flat parsing. So, like if we have a mathematical equation, let's say 2 plus 3 into 5. So, multiplications is more tight than addition. It has a higher binding power than the addition operator, the plus operator. So, multiplication is given higher precedence than addition. So the result is that AST stripes away all punctuation constraints like semicolons and parentheses, keeping only the pure raw logical intent of the code. Next slide. And final part is the C code generation. So we have this abstract syntax tree. So we would perform a depth first search on the abstract syntax tree, and starting from the root and driving into all the child nodes. And we assemble this into corresponding C statements. And now we have the C code, it's written into a C file. So we can invoke GCC or Clang by creating a child process. And yeah, we get the executable of the C code. That's it. Over to Tanishq. Thanks.
Thanks, Abhishek. Now let's zoom in on exactly what our team accomplished over the past week. We focused heavily on building our foundation and understanding theory for our project. First, we tackled writing formal rules. We learned how to write EBNF specifications so we could formally define the grammar of a new language. Second, we ramped up on the system programming in Zig. We spent the time understanding the basics, specifically how to handle memory allocation and leverage Zig safety features. Third, we mapped out our pipeline architecture, learning exactly how data can most efficiently flow from a raw text file into the structural language tokens. Can we move to the next slide? With theoretical foundations set, here what we'll be building in the next coming week. First is the lexical tokenization. We are building the actual scanner that will accurately transform the raw source code into distinct stream of defined grammar tokens. Second is error diagnostics. We are implementing descriptive compile time error reporting. If there is syntax error or malformed code, our system will track the precise line and column coordinates to make debugging seamless for the end user. Finally, we will be deepening our practical jig experience and getting hands on memory management by working directly with Arena and the general purpose allocator. That covers our project. Thank you. If anyone has any question, they can ask our team.
Um, to answer Vinayak's question, so we have just designed the basic EBNF grammar and also 5 sample programs, which we will be working on even more in depth, so that we can have more clarity on building, making it easier for the lecture and parser. If you want, Yeah. So I think Sarah's question is, I think, what's your plan with when C semantics don't map cleanly onto a language feature you want? Um, so if a feature is there in our language, which there's no equivalent in C, we just don't map it. We'll try to implement it in supporting runtime library. We'll either use some helper functions or we'll bridge the gap somehow. I mean, we deep dived into parsing the EBNF and tokenization yet. We just tried to learn the basics and the theory part so that we keep a fundamental strong. Yeah, yeah. Yeah. So I think question was, have you looked into how to parse? Yeah, yeah. So we just deep dived into how do you write the EBNF grammar rules, and what is a parser, lexer, and how do you get started with it. So we have just built the foundations. We'll deep dive into them in the upcoming weeks. Yeah. So any more questions? So yes, that's all the questions. Thank you, guys. Thank you.
Thanks, guys. I think we can move on to barely learning next.
Hope you guys can see the screen.
Yes, we can see your screen.
So, hello everyone. We're here to present our week one progress on barely learning, which is based on the research paper Learning to Play Donkey Kong using neural networks and reinforcement learning. So, our goal here is to train an AI agent that can successfully complete the first level of the Donkey Kong game. Now, instead of manually programming the Donkey Kong game to say jump here or climb up, climb here, and all of that, we want the AI agent to learn all of these behaviors on its own. Now, here we're trying to achieve these by methods of imitation learning and reinforcement learning. Now, instead of the original Donkey Kong game, we're gonna recreate only the first level of this game. Now, this recreated version will have 7 actions, which will be the walk left, walk right, or jump left, jump right, and all the climb up, climb down, or stay stationary. And another feature would be the 50% chance at which the barrels will roll down the ladders. Now, this will introduce a factor of randomness, which means that the AI cannot simply learn the sequence in which the barrels roll down, and it has to actually figure out new strategies to work when the barrels paths change.
So this is this is how something called as a multi-layer perceptron looks like. This is the neural network architecture which we'll be going with for this project. So it involves one input layer, one output layer, and a bunch of hidden layers. Here, preferably 1 to 2 layers. So for the input, what we have is we have 3 vision grids, that is 3 7 into 7 grids, and these 3 grids are stacked upon each other over here.
If you're
And
talking, we cannot hear you.
uh, can you hear me now?
We could hear you before.
Uh, uh, can you hear me now?
Yeah, we can hear you.
Okay, just let me know if there's any problem. Yeah. So we have something called as the vision grids, 3 grids which are stacked upon each other. The purpose of each grid is to identify a particular object. We have barrels, ladders, and power-ups. So each grid does the job of identifying that. And you might notice that the grids are not centered around the agent. The reason being the game is more focused on what's happening above than below. So it doesn't really care about what's happening below. So we do that for efficiency. Next, other than that grid, we also have something called as the agent tracking grid. That is basically a grid which is spanning the entire environment of the game. And this is used to track the exact position of the agent. It tracks the location of the agent, and wherever the agent is present, that cell has a value of 1 and everything else has the value of 0. So other than these two grids, we also have 4 additional features. That is one, whether to check if the agent is next to a ladder to enable the climbing option. Then to check if the agent is climbing to disable the left and right and jump options. Then we have the parameter which checks whether the agent is holding a power up, and the power up time calculates how long has been spent since the power up has been got, and the total time of the power up. So totally we have 551 features. Next we have the hidden layers, and this is the place where most of the learning happens actually. So it can be 1, 2 or multiple layers. So what happens is it takes the input, it infers something from the input, and it passes on to the next layer. So as the input passes through these layers, we have some form of understanding as to what is happening. Okay, so there's a barrel coming, so we might have to jump next time, or we can go left side, or we can climb the ladder, something like that. It also introduces non-linearity with the help of activation functions, such as the sigmoid function and the rectified linear unit. The sigmoid function converts random scores into probabilities between 0 to 1, and rectified linear unit removes all negative values and only keeps the positive ones. Finally, we have the MLP output, which is the most important part of this frame architecture. The hidden layers give us a bunch of scores. So these are the 7 actions which the agent can take at any given point of time. So left, left, jump right, climb up, climb down, and stand still. We take these scores, put it into a function called as the softmax transform, and it converts it into a bunch of probabilities. From these probabilities, the highest one gets a value of 1, and everything else gets a value of 0, and we convert it into a vector called as a one-hot vector. So the one which has the value of 1 gets executed by the agent. Softmax transform has like this important parameter called as the temperature, which is seen here. So temperature basically controls how explorative or how exploitative the model can get. So if we lean towards the explorative side, all these graph bars will almost look similar. So the agent has an almost equal chance of doing everything. So it'll explore more options. It's better for trial and error. But if we go for the greedy option, what happens is these gaps which you can see, they get magnified even more. So 4.5 will be something over here. So it'll just exploit the functions which are like already giving it rewards. So that is not necessarily the best for exploring, but like it is good if you want to optimize for the best action.
Now, after training with the imitation learning, we introduce the RL framework. Now, here the agent is the Mario, while the environment is the Donkey Kong game itself. Now, at every step, the agent observes the current state and it chooses one of the 7 actions. And according to this action, it receives a reward from the environment. Now, there are positive and negative rewards for according actions, and also the AI works on 2 specific concepts here. One will be the policy function and the other will be the value function. The policy function maps states to action, so which basically answers the question of what action to make given a particular state. And then the value function would be to estimate how good the current state is based on the expected future rewards. Now, here the ultimate goal is to maximize the total future rewards instead of focusing only on the immediate rewards. Next slide. So, as mentioned earlier, this learning process will consist of 2 stages, which will be the LFD and the actor critic reinforcement learning. Now, LFD is the learning from demonstration, where like a human plays like hundreds of games, and then the system records for each and every game state what action it has to take. And based on this, the a neural network is trained, and this is basically a supervised learning. Now, after this pre-training, the system switches to actor-critic reinforcement learning. Now, here the actor chooses the action for the given particular state, and then the critic evaluates how good this action is and how it has improved the situation or worsened the situation. Now, this critic continuously provides a feedback to the actor, which will gradually improve the decision making of the actor. Now, combining these two learning methods, we start with while starting itself, we start with a strong starting point, and then the ability to learn from experiences is a lot more while combining these two methods. Now, this actor critic method consists of two separate neural networks. The actor, which receives the current game state and decides which action to make. This actor works on the policy structure, and then there is this critic, which evaluates each and every action of the actor, and then it works on the value structure. Now, this game is represented as a MDP, which is Markov decision process, which consists of states, actions, transition probabilities, reward from transitions, and importance of future rewards. Now, in this case, the states contain 551 features. There are 7 possible actions, and the discount factor gamma is set to 0.99. And it's set to such a high value because we're trying to give importance to future rewards than focusing only on the immediate rewards, so that as we proceed, it gets better and better. And the ultimate goal is only to reach the princess, and so we have to focus more on the future goals. Dia, you can
We are
continue.
using yeah. So in our model, we are using temporal difference learning, so that the model learns at every step from the environment rather than getting the reward at the end of the episode. This matters in our model because each episode takes 2000 steps to resolve. If we wait for each and every episode to get over, then the feedback will be received by the critic very rarely, and this decreases the efficiency of our model. Whereas TD learning uses immediate rewards and current estimate of the next state's value. As Pranavika said, the value of gamma is set very high to 0.999. This is the discount factor, and it controls how much future reward matters relative to the immediate reward. If we set gamma value close to 1, this means that the reward in the future still matters hundreds of steps earlier. So it gives the model direction on how to move forward and which actions to take. What you can see towards your right is the architecture of the game. Here, the environment sends the current state to the actor and the critic. This is the stimuli, and according to this, the actor takes out one of the 7 actions, which is based on the current state of the environment. The action is sent back to the environment, resulting in the transition to a new state, and the environment outputs a reward. This reward is sent to the critic. Next slide. Now that the critic has the reward, the value function of the current state, value function of the next state, and the gamma value, it computes delta t, which is the TD error. This value helps the critic decide if the current action was useful or it was not. Based on the delta t value, if the delta t value was greater than 1, the critic infers that the current action was useful and it reinforces the action. If the delta t value was lesser than 0, then the current action was not that great, so it is discouraged. And for the terminal states, that is when Mario dies or wins, we set the product of gamma and the value function of next state as 0 because this helps collapse the delta t value, and it also helps stop the loop. Lastly, this delta t value is also used by the critic to update its value function for the current state, so the critic knows how the game is running. Next slide. This were the results of the paper. The model was there were three models trained. The blue graph shows the model's results when it was run on the demonstration data, which was LFD only. And the yellow bar shows when the model was trained with ACLA for 1000 games. We can see that the fifth model showed significant improvement. Next slide. So what we plan to do in the upcoming week is we plan to explore Pygame and fundamental game engine architecture. We plan to build a simple Donkey Kong style environment and learn PyTorch to implement and train neural networks. That was our project. Thank you.
I think there's a question in the chat. Answering Vinayak's question, why not use an emulator with the real ROM? One thing is, yeah, there's like copyright stuff, and then the code is hidden and stuff. But like, if we build it, if we build the environment from scratch on our own, it gives us much more control over the different parameters of the game compared to like using a ROM.
So Vinayak had to leave, unfortunately. So if it's possible, if you could, reply to him in chat or something, that would be great.
Okay, cool.
Yeah, so I had a question. I believe you mentioned somewhere that you're using Sigmoid, right?
Yeah.
Yeah, so why, like, I just had a question of why Sigmoid and like why not Tanich or something? Yes, here.
The thing is, it's not what do you say? It's not absolute that we have to use sigmoid or Relu. Like, this is something actuation function can be like experimented around with. So one fun fact is that these models which were trained here, right? They give varying results, but the second model, fourth model, and fifth model they use Relu, and the first and third model they use sigmoid as the activation function. So it is not absolute that we have to use sigmoid function. We can turn around to different functions also. So that is a part of the trial and error process. So as for using the paper which we refer to use these two functions. So we just took that as the reference.
Oh, okay. So you just took it out of like the paper used Sigmoid, so you continued with it.
Not necessarily. Our scope is not exactly not just replicating what the paper did, but like to improve on the paper. Like we find out that the paper wasn't actually successful in what do you say, improving the model. If you see the graph, right? So our scope is not limited to just what the paper has done, and then we do plan on experimenting with stuff to increase the yellow bar on the right side.
Right. So, yeah. So, which kind of comes back to my question of like, did you like look into maybe using Tanich or something like that, or like, I just want to know like, why did you prefer Sigmoid over Tanich?
Right. So I'm guessing what the people who wrote the paper had in mind was like, you use the ReLU function to take off all the negative values, and a sigmoid function, I'm guessing it's because of the probability thing. See, we want all these scores converted into a clean probability which add up to 1. So sigmoid kind of helps on that aspect. It converts the thing into something between 0 to 1, and if you add up everything, it's like unity. As for tanh, it would go from -1 to 1. I think that would like increase the complexities. Does that answer your question?
Um, okay. Up to some extent, sure. Anyway, there's a follow-up for your conversation, for our conversation in the chat. Hemant says, why not use softmax as an activation function since each action is independent?
Okay, that's a good question actually. Wait. The reason why we don't use softmax in the activation function is because uh, softmax, we are using it like if you see this what do you say, this framework, right? Where we use softmax is somewhere over here. Like see, the environment gives the stimuli, actor somewhere over here. So the actor gives out the values, and the values get converted into probability, and then yeah, somewhere over here we use softmax to convert it into the respective probabilities, and the one hot basically gives the action. So when you say the hidden layer, the sigmoid function, that would act somewhere over here. So I'm guessing it's more of a two-step verification process type of thing, where like you kind of make sure that the values, the scores are like properly represented as probabilities. Right. I hope that answers the question. Okay, as for the CNN based approach, uh, we can try that actually. But like as I said, in this current project, we are representing we are not exactly taking the raw image or the pixels, but we are taking it in the form of like a bunch of 551 features and vectors with values, and MLP is more suited for that one. So if we do try CNN, we'll have to like change up things a little, and we'll have to extract take the raw pixels and raw images rather than the values which we took here. We can try that depending on how fast we can get done with verifying and improving the results of the current paper. Yeah, exactly. What Hemant has told here. The current version like tries to minimize on the complexities as much as possible. Okay, then. Thank you, guys. And if you aren't satisfied with my answers, I'll get back to you later in the chat or through DMs. Thank you again.
Yeah. So next up is Repolence. If someone could start sharing their screen, that would be great. Perfect.
So, good morning, guys. This is Prajwal. So, we are from the project Repolens under the mentors Navya, Arjun, and Ananya. So, if you have been following AI over the past years, you all must have certainly heard about the term RAG. It became so popular that it seems to have found its way into almost every AI project and even a lot of resumes as well. So, RAG, which stands for Retrieval Augmented Generation, it's basically a kind of pipeline wherein instead of expecting an LLM to know everything, we first retrieve the relevant information from a knowledge base and then provide the information to the LLM before it generates a response. So this allows the model to answer specifically based on the given context rather than relying on only what it learned during the training. So in this given flowchart, you can see there's a PDF of maybe Jayanagar Zomato reviews as the source data, and then it undergoes a pipeline which involves chunking and then embedding those chunks into a vector database. And whenever you receive a query, you again embed the query, use a similarity search, maybe cosine similarity, and get the top k chunks which you want to retrieve, and then send it to the LLM, which will then give you a response based out of the context. This is one good example of a RAG. And RAG has countless practical applications. So we asked for ourselves, what if we could build a RAG specifically for code bases? Like imagine pasting a GitHub repository and asking questions like, I want to understand the routes of this applications. Where do all the endpoints live? Or like, how does the authentication flow through this project? Or even summarize the architecture of this repository. Um but again, we all knew that every LLM could do this. Like you could just give in a file and then ask it to summarize. So but we want it to be different. What if your project spans across multiple directories or folders, 40 different folders for example? So that is not feasible in order to push everything to an LLM. So that's exactly how we came up with the Repolence, a RAG designed specifically for code bases. However, we quickly realized that this traditional RAG pipeline works exceptionally well for PDF or articles or maybe documentations which involve text. But source code is fundamentally different. Normal RAG would generally fail because similarity search will not find any relevant code snippets or things, and chunking will destroy the code structure. Maybe your function gets cut off in half or the classes are broken. So we started the research and found something interesting called PageIndex, an open source project which uses no chunking, no vector database approach, and still manages to outperform standard RAG. Like for huge documents spanning across 1,000 pages, it is way more faster and accurate than a traditional RAG. But what we found actually interesting was instead of searching the top k chunks based on the similarity and it retrieving them to the LLM, this uses replaces the vector search and uses a hierarchical tree of document, and it allows the LLM to reason over the document by using the subheadings and stuff. But this again was not meant for code bases. In code, two files may never share the same keyword, or yet they be tightly coupled through imports and function calls, interfaces, and abstractions. So we had to come up with something better approach. So we because of that, the goal of Repolens isn't just to answer some isolated questions like in another LLM. The objective of Repolens is to build an understanding of the repository itself, the architecture, structure, dependencies, execution flow, and the relationship between the files. So we then came up with it builds a code hierarchical tree and adds dependency aware reasoning for complete understanding of the code base rather than just file level question answering. The complete technical overview of the project will be taken care by my teammate Harsh.
Yeah, so hello guys, my name is Harsh. I am part of the project Repolens. So, in our technical overview of the project, we basically use a tree sitter plus a graph approach. So, when we go through each file, we have our functions, and what we do is we take those functions and create a node out of it, carrying a summary of what that function does, and we add it as a branch in a tree, and that tree will have your parent file, and that will have its parent folder. And so, how do we connect all these? We use a graph method, which basically connects all of these all these dependencies. And basically, like let's say you import some function from a file in a different folder. So it will first go to the folder and then it will figure out the file and then the function. That will loop back to your original file, and that is what we are doing here basically. So when we create the final graph of the whole code base, we basically store it in a database. We've personally chosen Postgres. Now, we want to now there are different kinds of questions. I will be talking about how we classify those questions in the next slide, but we want to pass it. We want to pass it to the LLM, but we don't want to spend many tokens. So this is where we take the embedding and vectorization from the original RAG pipeline so that we can reduce our amount of context. Yes, we can move to the next slide. Yeah, so our node structure is here. We basically store, this is for each function, each file and each folder. We use the same structure. So the main important part of the object is the LLM generated summary. So basically, whenever we pass it to the LLM, it will process that and it will give us an output to the question. So as you can see, I have explained the structure of the tree in the previous slide, and this is how our tree basically looks like. Now we have kind of built a classifier. We will be building a classifier. It's not something like ML model related, like using random forest or light GBM or something like that. It's just basic if else condition. And we try and classify it under these two or three types of questions. One is summarize this repository or summarize this file, and that will basically pass through the tree and figure it out. Our overview, so let's say how this one piece of logic works and everything. Relationship between the files, this is where the graph comes in, and the location of a particular function or a particular file. So you can check how the retrieval methods are here, but it will be explained much more in depth by my friend. So I will be passing it down to my friends to explain the architecture.
Hello everyone, this is Anish here. I'm a mentee under the Repolance project. Our core rack pipeline is made of two components. First component being the tree index. Tree index is built based on the output given by the ASC. Basically, the files are under a folder. The components of each module, like class, functions, and identifiers. So, and our plan is, along with creation of a tree with nodes, each node will have an ID, a file path, and a type. Like, is it a constructor, is it a class or function? Then even a line range, like the range of a class or function. And each node also gets explanation from the LLM and what is the purpose of that in the given code snippet. The second part being the dependency graph. We have various nodes in the tree, but it is important for us to know how they're interlinked. If we don't know why they're interlinked, LLM will not be able to give a good answer to the user. So that is the main use of the dependency graph. Next slide. So this is the architecture of our project. First, the user gives a GitHub URL. The repo is cloned. With the help of the tree setter package in a Python package, we do get a tree. Based on the tree, the graph is made, meaning the dependency between the components. The graph is stored in a PostgreSQL database. Now the user gives a query. As Harsh explained, it is passed to a classifier, and times it is embedded into vector embeddings, and it is then stored in a vector database. It's passed to LLM, the final graph, and with that we get a final answer. Over to my friend Ishan.
Hi everyone, I'm Ishan and I'm currently working on RepoLens and I'll be explaining how retrieval works. So once the user query is passed, so we have to retrieve the right information. So in order to do this, we'll traverse to the repository and try to find the right nodes. As my friend had already mentioned, there are summaries of each nodes which are accessed, and the right summary is found and the right node is identified. For example, the user asks the query how authentication works. So first thing that happens is tree search, and the right node is identified. And using this, we expand upon the graph. So we identify which functions are called where, and this is where network X comes in. So in network X, there are things called as nodes and edges. Edges are the relationship between the nodes, and these edges can be assigned weights. So we can say how relevant this particular relationship is. And there's another function in network X, which we can use to identify the shortest distance. So using this, we can identify the most relevant information and send the right context to the LLM, and the code is retrieved, and the user's query is answered. Next slide, please. Yeah, so the tech stack that we're considering is tree setter for abstract syntax tree, and we'll be using NetworkX for graphing, and OpenAI or Gemini SDK for the summary generation, and the backend will be fast as API, and storage will be PostgreSQL Quadrant. And another thing that we had considered was using Neo4j, but because of the graph structure, but it provided no benefit over PostgreSQL, and we're already using NetworkX for graphs. So we just thought of going with Postgres. And the embedder will be Gemma 3, 300 million, and the vector database is Quadrant. Yeah. And the next steps are will be working on lightweight tree creation and node creation using tree setter. That's about it. This was our project. Thank you for listening. And if you have any questions, our team will be answering it.
Right. So were we that clear that there are no questions?
Okay. Seems
Yeah.
like there are no questions. If you guys do
Yes.
have any questions, be sure to put them in chat, and they'll get to you.
Sure.
I guess we can move on to the next.
Up next is NetStack, so you guys could begin.
Hello everyone, we are Team Nitstack. I'm Visruth Television from Nitstack Mentee. Now, our goal from Nitstack is to create a DIY TCP IP stack from scratch to really understand what goes under the hood. So here are our key goals. What we want to accomplish are to have IPv4 header passing, ICMP, TCP, and UDP. We will be our stack will be on top of Linux done virtual interface, which is provided by the Linux kernel, where you can just read the file to see the raw byte packets by through the network. Next slide, please. Okay, here's our roadmap. For the week one, we have refresh upon Git and GitHub. Then we learned about network concepts, OSI model, and the life cycle of a request. For week two, our deliverable would be for you to be able to ping our device. For week three is a UDP. You can now send UDP packets to our device. Week four, TCP, and week five, confirmed received packets. Okay, next slide, please.
Hello. I'm Aishwarya V, and I'll be taking over for the technical overview. So start discussing with like the most like few of like the basic concepts in networking. And let's start with the term which we all are familiar and we all use like an everyday basis, internet. So if you look at definition, then it would just be like collection of computer networks, and then they communicate with each other, like following a set of instructions called as protocols, and exchange data among themselves. But then the most unique definition would always be that it is a network of networks. So what exactly does that mean? A network basically is just a few devices linked together. And let's just say, for example, in a room, there are like few computers linked together using a certain Wi-Fi or something that would form a network. And then culmination of many networks would ultimately lead in formation of internet. So we know that now internet has like many devices connected with each other. So let's just say, for example, I am trying to access google.com from my device. Now, internet having so many devices, there's a thought that how would internet know that this certain device is trying to access a certain website and then a certain process in it? That's when IP address and ports come into picture. These two are like one of the most commonly used IP address and ports. IP address mainly helps in identifying which machine is trying to machine or host is trying to like where the message is going to or is trying to access what. While port is helps in identifying which process on that host is being mentioned. Now, remembering IP address for every single website is just really not possible. That's when domain names come into picture. Domain names are easy to remember names given to us so that we don't have to buy our IP address. But computer obviously doesn't understand words, right? It only understands numbers. So that's when DNS server comes into picture. This converts the domain name into like IP address, which is again used for reaching out to a certain website. So until now we've looked into like accessing a certain website, let's say google.com. But then how do we start communicating to that website? That's when clients and servers come into picture. Since I'm trying to access google.com from my laptop would act as the client. Now this client would send request to like the main Google server, and server would send a response back in like small packets, small packets where are like which are like small data units, not a whole web page as a whole. Now since we know that internet has many devices, hence many clients, and then many requests from like various places, how will server know like which is the best part so that client receives the information like efficiently or quickly? That's where routers come into a picture. Routers helps in finding the best path for like the information to travel. And this is just a small slide covering two vital topics, HTTP and HTTPS. As you all know that HTTPS is like used by most modern websites because the data here is encrypted. And like if you all see your websites, there's like a lock symbol that indicates that data here is being encrypted and is like very secure. While HTTP is like just plain text. Data is not really secure there. So I'll hand over to a bunch.
Vance is facing technical difficulties right now. Oh, okay, okay.
So
Okay.
I'll be covering the protocols and networks like layers required mentioned over there. Audible. Am I audible now?
Yeah, you're audible.
Yeah, yeah, you're audible.
Yeah. So I'll be covering the application transport layer and the network layer. So to begin with the network layer, this consists of IPv4, IPv6. This will handle the routing and the IP addressing, and the transport layer will handle the port management and the connection reliability. Next slide. So I'll start with the network layer. Uh, So this is an IPv4 example. As you can see in the diagram, there are 4 octets. So that is how an IPv4 address looks. So what is this IPv4? It's a connectionless network protocol. So to best describe it, I can say it as a best effort basis. It will try its best
Once you're not that audible.
or they are reliability. Am I audible now?
Since Wash is
Hello?
facing technical
Is it fine?
difficulties, we'll skip it to. Okay, so what I will continue with them. So we are here for IPv4. We can see that there are 4 sections. 4 sections of each size about 8 bits. Now this is the current standard we follow for networking. Okay, the next slide, please. So what is TCP? TCP lies on the layer 3 transport layer. So in TCP, what happens is the client sends a sync packet, and the server should respond with sync acknowledgement, and with that, the client sends an acknowledgement packet. So with this, you would have established a connection which guarantees that there is no packet drop. So that's why TCP used in the current HTTP 1.1. We are is using TCP. Next slide, please. Okay, UDP is fire and forget. So the client just sends a packet and it does not check for an acknowledgement or any syncs compared to TCP. And major application for this is in game servers, where you can always count on another stream of packets coming up. So you don't really care about the packet to come. So you can just overcome it. So next slide, please. Okay, now a life cycle of a request. So here what happens here is, so whenever you type google.com in the browser, first what happens is google.com is then transferred to your ISP. ISP goes to its domain name solution servers or a name server. Your name server will return the specific IP address, and using this IP address, your browser will will establish an TCP connection as mentioned before. Using this TCP connection, it will send an get HTTP request. So this will be then transferred to your Google server. Google server will pass this through, and return the response with a response header stating, okay, this is the protocol, this is the code, this is the content type, and the response payload, which is then rendered on your browser window. Next slide, please. Okay, what's next for us? For the next week's review, we are gonna make ping command work. So ping command should we should we should implement the ICMP protocol, that is Internet Control Message Protocol. So whenever you ping, you send a packet with specific information. Our client will then return you a specific packet telling it received the connection and this was this. So you could measure the round RTT round trip time, and that's it. That's it from us.
Yeah. So, okay, great. I believe the next one is silicon.
Yeah.
Carry on.
So, good morning, guys.
Do you guys see the screen?
Yeah, we can. So, me and Kritika will be presenting Silicon, and our mentors are Pranav and Suhas. So, Silicon is exploring silicon artwork through synthesizable RTL, which is a register transfer level, simulation, and open source tools. Next slide, please. Okay, so, introducing blog. Imagine if you're building a modern chip, microchip. It contains billions of tiny electronic components like switches, gates that we see on our slide. So if we try to do every single one of them by hand, it would take lifetime. This is where Verilog comes in. So Verilog is a hardware description language. So the word description here, it isn't like Python or Java where we tell a computer what tasks to run. Instead, Verilog is like a digital architectural blueprint where we write text called an RTL, register transfer level code, to describe exactly how you want electricity and data to move through a chip. So, as we can see in the diagram, you write the text code on the left, and a computer program automatically translates that text into complex physical circuit of gates on the right. In short, Verilog just lets us code hardware into existence. So moving on. Why do we need HDLs like Verilog? Now, so the main question is, why do we have to design chips this way? It's because manufacturing of physical chips can cost millions of dollars and take months. If you make a single mistake in a physical chip, the entire batch is ruined. So this is where Verilog comes in handy. So what we can do is we can simulate, we can design, and we can verify a chip entirely on a computer before we send it out to the foundry to actually manufacture the chip. So if we look at the steps of creating a microchip, we have all these main steps mentioned on our screen. So writing and simulation, we write the code, the Verilog code, and we run simulations to test it. If there's a bug, of course, we can fix it then and there, and we can write a more efficient code. Synthesis is when it works once it works perfectly. Software automatically translates our code into a map of actual electronic gates, a process called synthesis. And then finally comes the physical layout, where we map out where those gates are physically present on the silicon and safely send it off to become an actual product used by various of our machines, be it computers, mobile phones, etc. So moving on. Okay, so the difference between Verilog and other software languages is pretty simple. We have to understand that Verilog is not like normal programming where we have all these certain ways that things work. So building the brain versus giving instructions, like in Java or C, you are writing a list of instructions for an existing computer chip to execute. Whereas for Verilog, you aren't really writing the software, but you are designing the hardware on which the software works. So there's another difference between Verilog and those software programming languages is where the codes written, they are step by step executed on software level, but for a hardware level like Verilog, all the code is executed at the same time. But that's not usually true all the times. It does happen sequentially at some point, but for the most part, it happens consecutively. So, next comes the concept of time, where we see that in Verilog, we are given the advantage of making time delays in our code. So we can tell when the code has to be executed at a certain point of time. But in normal programming, we don't really have such advantage where we can tell when the code has to run. So that's another fact about Verilog. And yeah, so that's about the differences between Verilog and the software programming. And of course, there's also the data types where we have wires, registers, logics that represent all the physical connections on our chip. Whereas for C or Java, we have different data types like int, float, objects, like the abstract memories. So Kritika will be taking forward.
Yeah, so let's now look into Verilog fundamentals. So before we actually start writing Verilog, we first need to understand how it's organized. Like any other engineering design, there's proper structure to flow. We can broadly divide Verilog into four main areas: structures, data types, behavior, and operations. First, the structure. Instead of building one huge circuit, we design into smaller modules and connect them together. This makes it much easier to understand, expand, and reuse. Once we have these modules, we need to communicate. That's where data types come in. They define how signals are represented and carried through the design. But carrying signals isn't enough. We also need to describe what the hardware should do when those signals are present. Behavior describes how the circuit reacts when the input signals change. Finally, we have operations, which are the operators used to perform calculations, comparisons, and bit manipulations to build the required logic. So these four areas form the foundation of Verilog design. Now let's start with the first part, how a Verilog design is organized. Everything in Verilog starts with a module. You can think of a module as one functional block that performs one specific task. Instead of creating one large design, we split it into smaller modules. This makes the design easier to build, understand, and reuse. Now, if we have multiple modules, they need a way to communicate. That's why we use ports. Every module has inputs and outputs. Inputs brings us signals into the module. The logic processes those signals and the output sends the result to the next module. So ports are basically the communication interface between hardware blocks. Once the signals enter the module, we use operators to process them. Verilog provides arithmetic, logical, relational, shift, and bitwise operators. Since hardware works with binary data, bitwise operators are used very frequently. These operators combine to form expressions that eventually describe the hardware logic. Now we know how the design is organized. The next question is, how are those signals represented and how does the hardware react to them? Inside a hardware design, everything revolves around signals. So before writing any logic, we first need a way to represent them. The two basic data types are wire and register, which is called reg. A wire simply represents a connection. It doesn't store a value, it only carries signals from one place to another. So it's commonly used with continuous assignments. A reg is used inside procedural blocks. Even though it's called a register, it doesn't always become a physical register. The actual hardware depends on how the RTL code is written and synthesized. To describe how the hardware reacts, we use procedural blocks. These are the main types of procedural blocks. The initial block runs only once at the beginning of a simulation, while the always block is event driven and executes whenever a specific event occurs. Depending on how it's written, it can describe both combination and case statements to make decisions. They're conditional statements, so they must always be written inside an always or initial block. So overall, data types represent signals, procedural blocks describe how the hardware reacts, and if in case decide what action the hardware should take. Now moving on to VGA Playground. So VGA is basically Video Graphics Array, and VGA Playground is an online tool that lets us write Verilog code and instantly see the output on a virtual VGA display. Instead of writing a complete graphics program, we simply write hardware logic that decides the color of each pixel based on its current position on the screen. A built-in sync generator takes care of scanning the screen line by line, just like a real VGA monitor. So we only need to focus on generating the pixel colors. To get familiar with it, we first explored some existing examples like moving stripes and concentric things. We then modified things like color, thickness, direction, um, and speed to see how even a few changes in the slide. On the left side, we modify few details, and then on the right VGA display, we can see the changes. So this helped us build an intuition before we start creating our own design from scratch.
So, as Kritika mentioned about the VGA playground, as we saw, there was a written code on the left and a display on our right. Something like that we will be implementing in our next week as our plan. And we will be exploring how register transfer level can be used to generate hardware based network. And yeah, that's about it. Any questions?
All right, so I think we can move on to graffiti now if there are no questions.
All right, hi guys. I'm Arnav along with my teammate Narendra, and we'll be going on with graffiti.
Sorry, guys. I thought you could hear me. Sorry, I'm sitting outside. So, I apologize for any extra sounds. So, majority of the data that we deal with classical neural network basically goes with it's structured in tabular form in the form of CSV and other and Excel format. But if you look at the real world data, say in the form of social networks or atoms or molecules, these are represented by properties that can be held together in nodes and edges. And based on the properties of nodes and edges, overall properties can be inferred from a structure of a graph. So based on properties of the nodes and the edges, you can try to determine new connections, see how these whole models interact with other like the nodes within the structure, and based on that you can see how the entire graph is changed after some time. Next slide. So in yeah, as I said, with applications of GNNs, you could use for molecular property prediction, social network analysis. Zachary's Karate Club is basically like the hello world for a lot of graphical neural networks where you can distinguish between properties of the nodes and see how they split. Recommendation systems where you can see with in social media platforms where other user profiles are recommended to you, and citation networks where researchers basically can scan through the graphs of what citations have been used previously. Next slide. So the different types of GNNs depend on what kind of a project you're building on, right? So if you look at GCN, there are the different ones I've mentioned here. GCN is where you want to assign equal weights to all of your nodes without any regard to the features that they bring to the table. So and then the GAT here gives you a dynamic weight. So based on the embeddings of your node and the other nodes, you can be able to determine the dynamic like weight for each of these nodes to filter out the properties you would require for that one particular node. Graph stage is built to withstand dynamic structural change in your graph. Say, for example, GCN and GAT are transductive in nature, as in you train the entire model, and when you want to run the entire model on a new graph, on a new set of graph or new nodes that have come into the picture, your entire system would fail because it require the GCN and GAT require predetermined information so that your entire system can run together. But graph stage, based on a locality of nodes, can determine the properties of a newly added node, which helps it to adapt to dynamic change. So, and then graph isomorphism network is used for tasks which require higher expressive power, say determining the structure or the properties of molecular bonds uh, or the or the entire properties based on the structure of the molecules. Next. So the whole properties of GNNs is based on a neural network called message passing neural network. Here, after initialization of of all the nodes and edges with some features, you are able to basically formulate a message. Say in the given diagram, node 3, node 4 all compute messages that have the features from the source nodes. And also, while they're passed along to node 1, edge feature are also taken into consideration, and at the node 1, these messages which are received are aggregated through multiple aggregation functions, which will be covered in the next few slides. And you can then update the current node's representation or the values encoded in that node with uh, regard, like you can implicitly calculate them uh, like dynamically with the other nodes, or you can explicitly just set the nodes weights from the edges from the beginning. So based on that, you can update the property or the state of the one particular node, and this can be run over multiple iterations. Next. So aggregation, the like I said, the aggregation mechanism is one that you need to select based on your properties or requirements, right? So must be permutation invariant means that if you have I have a graph, right? If I have this graph can be represented in different structures. The nodes and edges can carry the same connections. Can you guys hear me? Hello?
Yeah, yeah. I can hear you. Yeah.
All right, thank you. So this graph can be modeled in different ways, as in the nodes and the edges can carry the same weight and the same structure, but it can be looked at in a different format, or its adjacency list can be represented in a different format, right? So if you the entire mechanism for aggregation should be in such a way that your functions that you're using for aggregation should not depend on how your input is structured or given into the graph, but it should just be able to work with different kind of graph representations and still give out the same output. So the aggregation mechanisms here, which are the simple ones, are sum, mean, max, which carry their own advantages and disadvantages. Sum adds in the total signal from all the neighbors that you get, and but that leads to an explosion in the numbers that are used for representation of that one particular node. Mean tends to disregard some features that might be important. So, which is why dynamic weighing for each of the nodes might be more important or more essential in the context of mean use as an aggregation mechanism. Max again also leads to an explosion in numbers and only keeps the strongest neighbor signal. So no aggregation mechanism wins universally. You have to use your preferred aggregation mechanism based on your inputs and outputs and the quality of output that you regard. So the most advanced in this kind of in this area would be trying to combine all three, using softmax and other such features to basically get a local idea of what your neighborhood looks like while without disregarding your features and keeping your numbers from exploding to higher values. So my friend Arnav will continue with the next few slides.
Yeah, so moving on to the formula of the message passing layer. So what is happening here is the actual mechanics of the message passing layer. So every node in the graph holds an embedding, and a node updates its embedding by looking at its neighbors. So here in the formula, hi at a layer k plus 1 equals to phi that is applied to the node's own current embedding combined with an aggregation of messages from its neighbors. So here phi is an update function, which in itself is a neural network and it's trainable. And a caret function here is operator here is how the aggregated messages concatenate, and the psi function here is basically the uh, relational operator between the neighbor and the node, neighbor j and the node I. And after stacking these layers, a node has absorbed almost all information from ki iterations, and the depth is directly controlled from the information that like it's traversing from. Now moving on to the limitations of GNNs. The first one here is over smoothing. So over smoothing occurs when we stack too many of these message passing layers, and each layer pulls a node's embedding closer to its neighbor's embeddings. So doing this many times makes the model lose its ability to tell nodes apart. And even though it has more layers and more parameters as the number of layer increases, it still lowers its accuracy parameter. This is actually different from what we have seen in convolutional neural networks, where depth and adding more layers significantly increases the accuracy. The next limitation here is over squashing. So over squashing is basically information from distant nodes gets compressed through a narrow bottleneck. So what happens here is the compression losses of information happens here. So as you can see at around radius of 4, the we can see a significant loss in accuracy. Um, yeah. So next limitation here is expressiveness ceiling. This is basically like if we run a 1WL test, that is basically an isomorphism test that looks for visual and visual comparison between two graphs. So here we can visually see that these two graphs are different, but the GNN models tends to not consider it as different because it can't reliably count basic structures like triangles and etc. So here the embeddings result is same as shown in the diagram. And this also results in scalability as a limitation because uh, uh, across multiple GPU training will be inefficient because there might be redundancy of graphs and the GNNs would consider it as a redundant graphs and not different ones. So what we plan for next week is, given the limitations, we'll read and build better understanding of neural graph pattern machines, and we'll spend the next week trying to build a small toy project on and building a small toy project that would expose the shortcomings of GNN and also exploring GPM as an alternative. And what we'll take away from graffiti as a whole, that by the end of this iteration of graffiti, we'll gain hands-on experience on implementing and comparing GNN architectures like GCN and GATS, and we'll also expect to learn good understanding of current methods in graph representation learning and domain, and applying GPM architectures to graph classification tasks. That is pretty much from graffiti.
All right, if there are no questions, we can move forward with Twix.
Is my screen visible? Yeah, the screen is visible. Hi guys, this is Team Twix. I'm Navya and I'm here with my team Sinchana and Aditya. I'm mentored by Hemant and Aditi. I'll be walking you through what our project is about and what we've actually managed to cover this week. Next slide. I'll start by explaining what self-supervised learning actually is. So as we all know, supervised learning usually works with labeled data. We try to classify or perform binary tasks. Unsupervised learning, on the other hand, it deals with unlabeled data. So we're essentially trying to cluster data or find patterns in data or actually reduce the dimensions we're working with. But self-supervised learning sort of combines both of these. We're looking at the best of both the worlds. So we get to work with unlabeled data, and we're also trying to work on a very specific type of self-supervised learning. We're looking at Barlow twins. Barlow twins, out of all the self-supervised learning methods we actually read about, Barlow twins seem the most lucrative. So we work with a single encoder and decoder network, and we also work with a very small batch size compared to what the other self-supervised learning methods were dealing with. Another reason for using self-supervised learning would actually be because of how expensive working with labeled data actually is. If we needed to actually label every item of a data set, it would be a very expensive process and would be quite difficult to scale, which is why we're actually sticking with self-supervised learning. Sinchana would be continuing with the next slide.
Yeah, so for the technical overview of our project mainly focuses on self supervised learning, where a model learns useful image features without requiring any labeled data. So, here, instead of relying on labeling and then classifying, we make models learn each and every details like curves, edges, details about the images. Now, so here we are implementing Barlow-Twins approach, where we generate different augmented views of the same image and pass it through the same CNN encoder. So, and while passing it to the encoder, we give it some pre-test task. So, as you can see in this image towards the right, we give it a proxy task. This task is given in such a way that we get exact features that we are looking for. And here we don't really work on getting the right output. We're just giving it some task to extract the features. And then we after this we pass it through our testing data set, which is labeled. This one, a testing data set which is labeled, and it is small in amount compared to the unlabeled data set. And now we start looking more towards the output. Yeah, so for progress, so far for this week we have learned mainly about basics and fundamentals. We learned fundamentals of PyTorch, including tensors, image transformation, autograd, custom dataset, and data loaders. And in terms of code, we have implemented image transformation, our custom dataset, and data loader. And we also had a discussion about choosing a proper license for our project. Yeah, so the main challenges that we have in front of us is designing a proper data set and choosing the right augmentation which is having right strength. It shouldn't be too strong or too weak. So we'll have to experiment on that. And our target for the upcoming weeks would be to understand and resolve all these challenges and building a Siamese neural network and training our Borlo twins model.
We'll be expanding more about the current architecture which the Barlow Twins paper actually is based on. So instead, we first start by feeding a raw image to the model. The model creates two different augmented versions of the image. So when I say augmented versions of the image, it means transforming the image. We rotate the image, or we blur the image, we add Gaussian noise, or we create jitters in the image. So once the augmentations are created, we essentially try to feed it to a neural network. So the neural network consists of both an encoder and a decoder, as you can see in the image. Once the augmented image actually passes through the encoder, we get a representation. The representation is then fed to a decoder, from which we get an embedding. So an embedding is usually a representation of an image in the form of a vector. So as you can see here, we get two matrices, ZA and ZB. So every matrix is essentially a combination of an image and an embedding. So every row represents an image, and every column represents a feature which corresponds to the particular image. Once we get both the matrices, we try to compute a correlation matrix. So the rows would represent features from image one, and the columns would represent features from image two. So essentially, we're trying to understand what the correlations between features from both the augmented images actually are. So the diagonal elements would essentially represent features which are similar features from both images, and ideally they would need to be closer to one. Because we're sort of trying to say that similar features from both the images are closer, and all the off diagonal elements need to be closer to zero, since we're trying to minimize similarity between different features. So as you can see in the image there, the loss function actually highlights the diagonality, what I was actually talking about. The first term represents the diagonal elements, while the second term represents the loss from off diagonal elements. Another point to highlight here would be the use of a Siamese network. The function f theta actually represents the Siamese
the function which is used in the Siamese encoder and decoder. Ideally, they both need to be same so that the model actually learns the same features. The weights of the model needs to be the same. Yeah, you can go to the next slide. These were just some questions we thought you would have after listening to us. Feel free to ask us any questions you have. Thank you for hearing us out.
And
I
that
guess.
brings us to the end of our presentation, I guess. Do you guys have any questions regarding this?
Well, seeing that there are no questions, well, actually, that brings us to the end of week one. Great job, guys. That's a very good well, introduction to your projects. And well, any questions that you're remaining to answer can be answered and later here or in your chat while pinging the person. And well, that is about it. See ya then.
Yep. Thank you everyone for joining. Have a good day.